Hello and welcome to Equity Education, the chemistry version. And today we're going to be looking at chromatography, and it's going to be short and sweet. Okay, so with chromatography you've got to remember certain keywords and how the processes work. It's pretty simple, I think it's pretty self-explanatory, so we'll get started. Okay, so chromatography is for separating compounds of a mixture. All types of chromatography have a stationary phase, which is a substance in a fixed position, and another substance that moves over it called the mobile phase. Okay, so you need to know different types of chromatography. So the first one is thin layer chromatography, which you may see abbreviated to TLC. So thin layer chromatography has a stationary phase, which is a thin layer of silica spread thinly over a glass or plastic plate and dried onto it. So my stationary phase is this thin layer of silica. Okay, so a spot of component or sample is placed on the TLC plate near one end. The plate is placed with that end just dipping into a solvent. Remember, the solvent is the thing that does the dissolving, which is the mobile phase, and which slowly soaks up into a thin layer. So it's going up our thin layer of silica. Okay, separation occurs by, and this is an important word, adsorption of components of the sample or mixture onto the surface of the thin layer. Components which are adsorbed less strongly move upwards on the plate more quickly or further, which makes sense. So if we have a component which is not adsorbed onto the stationary phase, it's not sticking as much onto the stationary phase, so it will move up the plate quicker. Okay, a lid is usually placed on the solvent tank, which is basically what we do our chromatography in, to stop the solvent from evaporating, and that's because they're usually quite volatile liquids or solutions. Okay, so a reference compound or component is often used in TLC for easy comparison. The chromatogram, so that's what we get at the end, is complete when the solvent front, put that in brackets because really it's the solvent, gets close to the top of the plate. Once the solvent has reached near the top of the plate, what we actually call it is the solvent front. Okay, the number of separated components is equal to the number of spots which can be seen. If the components are coloured, they are easily seen. Colourless components such as amino acids can be located by spraying with a suitable chemical such as anhydride, sorry, this should be a comma, or iodine. Okay, and the RF values, so we call this the retardation factor of each component, can be found by this calculation. So if we just go past this diagram, it's down here. So the RF is the distance moved by the component divided by, or the dot, like this dot here, distance moved by the solvent front. So this will be quantitative value, so something we've actually measured. Okay, right. I'm just going to give you a minute to have a look at this diagram because I'm sure you've seen it before. See if you can work out what's going on. Okay, I'm sure you can label these, but we'll label them together. So the whole thing is called a solvent tank. It's usually a beaker. This is the lid, not surprisingly, it just stops solvent evaporating. This is the solvent, and I need to draw on my solvent front, so let's draw it. Ooh, that should be straight, but it's not very straight. This is my solvent front, and this line here, usually drawn in pencil, this is an example of an unknown mixture, so that's what I'm trying to figure out, as well as this one. And this, on the right hand side, we usually put the reference component, so that tells us we can, well, that shows that we can easily check whether the unknown samples have the same components as the reference component or compound. Okay, so if I'm going to measure the RF, let's measure it of this one. So to measure the RF of this one, I would do the distance moved by my component, my dot, over distance moved by my solvent front. So RF is equal to delta X over delta Y, and as we previously said, this will give us a quantitative value, and we can look this up in a data booklet, which is what we're going to describe next. Okay, so this is our diagram, and we will move on. So, okay, it may be possible to identify components using a data book of RF values if different components are similar to each other. If different components are similar to each other, so it means in structure they are likely to have similar RF values, so they may not separate and cannot be distinguished. Compounds with similar structures, such as esters, are very difficult to distinguish for this reason. So if we go back up, maybe we don't get these clear dots here, maybe they're mixed together. So we know that there should be some components separating out, but because they have similar structures, they don't separate out because they're adsorbed at the same rate onto the stationary phase. Okay, so moving on. Our next type of chromatography is gas chromatography. Ooh, just about enough space. It's used to separate mixtures of more volatile components. It uses a long coiled tube inside an oven. The inside surface of the tube is usually coated with an oily, viscous liquid, which is usually an alkane. This is the stationary phase. Okay, the mobile phase is an unreactive or inert gas such as nitrogen, or soluble gas. Okay, so a mixture is injected into the tube near the one end, and different components take different times to pass through to the other end. This depends on their relative solubility in the viscous liquid, or in our stationary phase. Right, so this is another key word. TLC acts by adsorption, so that's the method of separation. Gas-liquid chromatography, to give its proper name, is relative solubility. So how much the component is soluble in this viscous liquid. This is sometimes referred to as the partition. The more soluble they are, so the more soluble the component is, the more time taken to pass through the tube, which makes sense, because if it's dissolved into the liquid, which is our stationary phase, more than other components, it's going to take a longer time for it to go round the coil and then come out at the end where it reaches detector, which we'll talk about in a second. So the retention time is the time taken for a component of a mixture to pass through the gas chromatography column. Sometimes the stationary phase is a solid. The method of separation would then be adsorption. So the same as our TLC, but to be honest, this is a lot less common, this one, gas chromatography with a solid stationary phase. Usually you'll be asked about gas liquid chromatography, which has a method of separation using relative solubility. Okay, so moving on. Gas chromatography has similar limitations to TLC, as similar compounds will have similar retention times. Therefore, it may be difficult to distinguish them. There is a detector that records the appearance of components at the far end of the tube. It plots peaks on a graph called a chromatogram. The peak areas are related to the amount of the components, or the percentage of the amount of the components in the mixture. The time taken for a component to pass through the tube is called the retention time. Again, we're repeating what we've just talked about previously up here. This depends on the gas that is used, how rapidly it flows, as well as the temperature of the oven. Okay, to calculate the relative amounts of a component in the sample, the following formula is used. Okay, so you're going to get these peaks, and to calculate the area of, basically, it's a triangle, we would do half base times the height. Okay, so separated components can be passed into a mass spectrometer, which is known as gas chromatography mass spectrometry, or GCMS, which records their mass spectra. Components may then be identified from their molecular ion peak values, and I haven't got enough space to write that, so we'll just write the MR values. Remember, when we're talking about mass spec, it's really a molecular ion peak because we've knocked one of the electrons off. It's the MR values and the fragmentation patterns of the ions, all by using a computer to compare their spectra with those in a database. If you're unsure how mass spectrometry works, there's a separate video that you can have a look at. Okay, so GCMS is used for used in well, I don't know. GMC is used. Excuse me, there's not enough space to write this. In airports for security, and in forensic science and analytical science, e.g. testing athletes for banned substances. The GC detector will plot the results to produce a, as we said before, chromatogram. Chromatogram. A typical chromatogram is shown below. Right, so I've given you the axis, and then look, something like this. You may be asked to sketch this. Ooh, that's a bit of a rubbish. Something like this. It's quite hard to do it freehand. I may change this one a bit. Oh, I'll change all of it then. Should be more of a peak. That's a bit better. So something like this, where my x-axis is time, usually in minutes, and this is the response recorded from the detector at the end. Right, so this is what my chromatogram from a gas liquid chromatography may look like. Okay, so I can tell from this that there are 3 components in the mixture. And how can I tell that? Well, because there are 3 peaks. Peak A, peak B, and peak C. So what can I tell from peak A? Well, I can tell that it has the shortest retention time. So if it's got the shortest retention time, that must mean it hasn't dissolved much into our stationary liquid phase. Therefore, it has a low relative solubility in the stationary phase. And conversely, C has the largest retention time, so the time taken for it to pass through the gas chromatography column and reach the detector, so it must have the highest relative solubility in our stationary phase, which is the liquid stationary phase. Okay, so sometimes you may be asked to work out the percentage composition of a component. So we'll do it for A. So I might have to work out this percentage composition of A. Well, what I'd need to do is I'd need to measure my distance here and half the distance. So this is the half of the base times by the distance or the height of my peak. Yep. So to work out my amount of A is equal to the area of peak of A, and therefore half base times height. And if I wanted to work out the percentage composition of A in the sample, let's put the sample to make it make more sense, I would use this formula. So area of peak A, so I've calculated that using half base times height, divided by the total area of all peaks times 100. Let's make that a bit clearer here. Now I'm sure you know how to do this, so there isn't going to be any questions on this paper because it's pretty straightforward. So to work on my percentage composition of A, I'd find this area using half base times height plus this area of B and C and divided by the total area of all peaks and times it by 100. Okay, very lastly, so just a quick reminder. So chromatography type, we'll do TLC, and we'll call this GLC, let's call this GC. So in TLC, the stationary phase is the silica on the plate. Mobile phase is my solvent, and the method of separation is adsorption. These are your key words. GLC, so gas liquid chromatography, so the stationary phase is the liquid, usually alkane, so a viscous liquid. The mobile phase is an inert gas, usually nitrogen, perhaps a noble gas, and the method of separation is relative solubility. And I've put GC, so we'll put that the stationary phase is a solid and the mobile phase is an inert gas, and this method of separation would be the same as TLC, which would be adsorption. But I'm going to put a star here, okay, and say this method is not really assessed. I haven't seen many questions about this method. So if I were you, I would just remember these two top ones. So thin layer chromatography and gas liquid chromatography, or usually it's just referred to as gas chromatography. Okay, so the important words to remember, we got TLC, thin layer chromatography. You've got to be able to work out the RF value, which is the quantitative value. The method of separation is the adsorption. The stationary phase is a thin layer of silica on a plate, and the mobile phase is solvent. GLC, gas liquid chromatography, the stationary phase is usually a viscous liquid alkane. The mobile phase is an inert gas such as nitrogen or a noble gas, and the method of separation is relative solubility. And just as a quick point, because I haven't mentioned it, so in gas liquid chromatography, the retention time is my quantitative method. It's my quantitative method. So similar to my TLC, RF is my quantitative method of analysis there. In GLC, the retention time, this thing we've measured, is also the quantitative method. Okay, so no questions today. As long as you remember the key words, you should be able to do this. But as usual, I hope this was helpful, and I will see you next time. Okay, bye-bye.